In the early days of networked computing, protocols like TELNET established a novel capability. A user sitting at one machine could type commands and execute them on an entirely different computer located miles away. This client-server dynamic was highly asymmetrical. The terminal on the user's desk was a passive monitor and keyboard with no internal processing power. It simply sent requests over a wire and waited for a distant machine to provide a response. All of that processing happened inside centralized master hubs. Entire floors of buildings were dedicated to housing monolithic mainframes that kept an organization's compute power and physical data in one specific, isolated location. This reliance on a single location created a precarious bottleneck. If a hardware fault or a power loss took that central hub offline, every remote terminal connected to it immediately went dark. The entire system rested on a single point of failure. As the early internet expanded into a global public network, millions of users began hitting those centralized servers at the exact same time. The traffic volume broke the existing hardware logic. Relational Database Management Systems, or RDBMS, required data to live in strictly linked tables. Because you couldn't easily split those tables across multiple machines, the only way to handle more traffic was to scale up, to buy larger, vastly more expensive hardware to expand the server itself until it reached its physical limit. Compounding the hardware limits, these databases required rigid, predefined blueprints for data entry. As the internet began generating a flood of messy, unstructured information, like multimedia files and varied sensor readings, these strict schemas were unable to adapt. When the incoming data load finally overwhelmed the CPU or memory of the master server, the machine would crash. Without a backup system ready to take over that exact processing load, access for every client on the network vanished instantly. Between physical hardware scaling limits, the rigid database constraints, and surging global web traffic, relying on one master remote server became a mathematical impossibility. To process this new volume of traffic, architects moved away from the single supercomputer. They moved to horizontal scalability via NoSQL databases, taking the massive dataset and partitioning it across a cluster of commodity servers. Looking at this network topology, we see Apache Cassandra's masterless peer-to-peer architecture. Instead of one primary server managing a fleet of subordinates, dozens of identical nodes form a decentralized ring. Every node actively receives incoming data packets simultaneously. There is no central master routing the traffic. Because every node plays an identical role, any machine in the cluster can accept a read or write query from a remote client. If one or two individual nodes drop offline, incoming queries instantly reroute to healthy neighbors that hold replicated copies of the data. By making every node identical and distributing the workload equally, the single point of failure is removed. The network can continue processing remote requests even while multiple servers are down. Curious tone. Distributing data across 50 different servers secures it, but it creates a logistical hurdle. How do you run a calculation on a database that has been shattered into pieces?
As we can see in this visualization, the MapReduce framework solves this by running calculations in parallel. Instead of pulling all the data to a central hub, it fractures the massive processing task into hundreds of smaller, independent operations. In the map phase, the system divides the massive calculation and assigns the smaller subtasks to the local worker nodes where the data actually resides. The nodes filter and sort their assigned data subsets locally and simultaneously. Once the local filtering is done, the reduce phase begins. The database automatically collects those intermediate findings, groups them together, and condenses them into a single, final aggregated answer to send back to the user. This approach reverses the old client-server model. Instead of bringing massive amounts of data to a remote program, the system brings the program directly to the distributed data. All of these distributed clusters still rely on a network connection. But remote access often has to function in the field, where a device might lose its cellular signal and get cut off from the decentralized ring. To solve for offline environments, engineers built mobile databases. Systems like SQLite are resource-optimized databases designed to live entirely inside the local memory of an edge device. The client can read, write, and modify records while standing in a dead zone. The moment network access is restored, a synchronization gateway takes over. This layer batches the local offline changes,
compresses the data, and pushes the updates back to the central enterprise server. This local execution extends to corporate analytics as well. Using desktop OLAP or DOLAP, users can download multidimensional data slices directly to their computers, allowing them to run complex trend analysis while entirely disconnected from the corporate network. Remote access no longer demands a continuous wire to a master server. The actual capability to process, store, and query data has migrated directly to the edge with the user. Originally, remote access meant sitting at a passive terminal and typing a command. The network sat completely still, waiting for a human to initiate requests. Today, active databases replace that passive storage with self-monitoring intelligence. The database observes its own internal state and triggers automated operations the moment specific conditions are met in the data. This infographic maps out the Event Condition Action, or ECA, logic loop. An internal database trigger watches for a specific event, like a stock quantity being updated. It evaluates a condition, such as checking if that new stock quantity has dropped below a minimum threshold. If the condition is true, it executes an action. That action might be an automated script that instantly generates a purchase order to a vendor and sends a low inventory alert to management. These triggers execute complex corporate actions entirely on the server without a human client ever logging in or typing a query. Millions of these automated logic loops run continuously across dense, interconnected server racks, communicating with field devices and distributed clusters around the clock. The original ambition of connecting a remote client to distant data remains, but it has evolved into a global web where code and storage live everywhere at once.